Are you guys excited to talk about some lab stuff and pipeline? Yeah. I'm being cheeky here with the name, but it's basically what's coming up in labs, what are some of the new cool stuff we've been working on, and some of the new cool community contributions. As you know, labs has always been a place where we work with the community and bring the best stuff to you guys. So this is a brief overview of what I'll be talking about today. Most of the stuff will be some cool new advanced technologies. Some of them are actually quite advanced, that they are the cutting edge of the industry. But most of them are about pipelines. I mean pipeline in a kind of dual sense, not just tools that bridges one application to the other application or the stuff that pipeline TD works about. We also cover pipelines that applies to artists, the cohesive workflow from beginning to the end. As you know, Houdini are traditionally quite difficult. So we've been putting a lot of effort in figuring out how to develop tools and pipelines in a way that has a bit more hand-holding, a little bit easier for people to get into. So in that mindset, we started Project Dryad, which is a biome toolset. Actually, we started the conception of that quite a long time ago when Paul Ambrosius was still here with me on the team, and we kind of hatched out the idea of how that's gonna go. Later, Danica from my team, she took over. Then the rest of our team, we all joined in, especially towards the launch of 20.5. We all worked on Project Dryad at the same time. A spin-off tool from that, a smaller in size but equally useful, is point cloud instancing. As you know, PCG has been taking over Unreal and whatever community that's using Unreal Engine for the game development. So we wanted to make sure that we have good support for PCG. But there's more than PCG that we can do. And in that section, I will also talk a little bit about just the pros and cons of what do we do with PCG when we have Houdini, what is the best way to approach that problem. And I will be honest with you, I'm not trying to sell you Houdini, I'll be honest with you, what is the best approach. Then we're gonna move into three very cool plugins. These two are from Biomes consultancy, from Paul. The first one is Perforce for Houdini, so source control. And the second one is for procedural terrain, like Gaea 2.0. Some of you might have already seen it. Also, Paul did do his own standalone presentation 2 days ago, so I will just briefly mention them. You can watch the detailed breakdown of those plugins in his presentation, Plugin Mania. And the last one is ZibraVDB. It's very cool for VFX compression and rendering. So let's get into Project Dryad. At the core of it, what Dryad is a biome system. And what I mean by that is it's responsible in Houdini to place pipeline assets and pick them and set their attributes accordingly. It's currently not responsible for generating the assets. You may get your asset from your own generator or your own modeler, or even like scanned assets. But the point is, how do we place them in a reasonable fashion that looks realistic? So what do we mean by realistic? We'll get into that in a bit. It is not a constraint. I mean, realistic as in high quality, not as in realistic. You have to do a realistic game. As you can see here, you can plug in stylized asset. You can still get a beautiful scene. Put in some nice lighting. Everything is nice. And same here. If you use scanned asset, it's almost like the same environment. You swap out the asset, you get a different vibe entirely. Now, the burning question is, we know biomes are done in so many different ways in engine directly, especially if you have a AAA studio, they have their own engine. Sometimes they invest in very handy-dandy like in-editor paint tools with brushes, masks. Why do we still want to do biomes in Houdini? So the first thing is the quality bar, especially for people who are passionate artists who want to create the best results, or for non-game studios like VFX, or virtual production, where their bar has traditionally been pretty high. So we want to make sure that we have a tool set that's not just for games and for stylized game, but this is a very flexible tool set that everybody can use. And the benefit of with Houdini, as you all know, is that you can customize everything. There's no limits. So if you have an engine solution, it is fast. However, if you want to edit something, you have to borrow your engineer, and it's rather complicated. The other one is iteration friendly. So whenever you consider hand paint anything, it is fast when you do it, but if your underlying system needs to change, the map needs to change drastically, it's suddenly have to redo work. And we begin to realize the reality in the industry is not that it's going to take more time. It's more like it's going to take so much time, the artist will refuse to do it. Therefore, you just don't do the iteration. And as we know, game how they sell is not directly tied to how beautiful the art is. It's often how good the gameplay is. How do you get good gameplay? You need iteration. So even though we're so far down the pipeline where we're dealing with software, I think something that we're doing just by helping people can iterate faster in a more friendly way, in a more scalable way, we can hopefully make the gameplay better and people enjoy the game more. And third one is it's not your scale issue. It's not a skill issue. It's a scale issue. Sometimes when you have a massive world, how do you handle that? Do you need the ability to handle massive amount of data or to segment them into different tiles, or not necessarily rigid tiles, but just like multi-threaded processing is pretty good. So we already have this architecture and we have a whole team maintaining that. So if you leverage our architecture, it might save you some time from like building your own solution every time. And needless to say, Houdini is good at handling complex dependencies. So if you really want to have something really beautiful like that, I'm not trying to tweet up my own home. We did that ourselves, but there's a lot of different layers of procedural things goes into it. So if you ask me to reproduce that by hand painting that in a game engine, or even use simple logic like identify surface normal, or identify concavity or occlusion, it will not cut it. There are some simple operations that every engine can do, but there is way more in-depth stuff that goes into just simple geometry analysis. We also have to acknowledge the challenges. It's not like doing Houdini is good, therefore just go into it and you're never going to run into a problem. We know what problems you might run into. For instance, if you want to transfer data between Houdini and your game engine, you might have a data transfer speed. At a certain point, it will become problematic for you. And our plugin team has been working very, very hard on this and improving how they build Houdini engine, how they structure the memory sharing, the communication. So it's getting faster. But also people have their custom solutions. Maybe they don't necessarily go through Houdini engine. They can go through custom JSON format or some other CSV format to bring the data in. What I'm saying is that there are solutions to this. It's not a deal breaker. A second thing, if you feel like your cooking is taking too much time, there might be opportunities to optimize your swap network or your PCG network. Just do the design of the tool better, and it's also not a deal breaker. Artist friendliness, that's really a lot of it is on us as a tool builders to really make sure to talk to you guys to understand what is the best way you want to use these tools, so that we don't build them in a silo. We consider all the kind of variations you want to interact with the tool set. So I don't want Houdini to have a reputation of it's too scary to artists, that kind of thing. We're working on solutions to that. Persistent override is something people bring out all the time whenever we talk about biomes. Like, okay, you have your procedure system, now I need to manually do something. Then if I re-click something else, will my manual override persist? So what I'm trying to say here is this is a very important point. We'll keep that in mind when we design our system to make sure that there is actually a way for you to do your override and not get them erased when you re-click your whole network. Pipeline overhead, that's like on a studio level. You might get pumped up by all the other stuff I talked about, but if you're thinking about who's going to build this system, there are success stories in the past by very massive studios, and they can build very beautiful, very powerful Biome toolset or toolset like that. And for your own studio, whether you're big or small, you're looking at that, you'll be like, that's very nice to have, but now I need to have a conversation with many people in my studio. Do they actually believe in this? Do they want to pay for the overhead? That is actually a core motivation for us to build this tool at Labs for you, so that you don't have to invest so much overhead. We'll try to tackle on something a little bit big this time, so that you can get it and just use it out of the box. Now, let's start with a bit in depth. How does Biome work? I want to talk about this a bit high level because this is not a super long presentation. I'll just talk about like how you want to understand this system and how you want to use it in general, and not get into some nitty-gritties of the parameters or stuff like that. So if you think about you want to author a biome, obviously you have your terrain. That's easy to understand. Map is a little bit broad concept. Map could be literally like a map you paint in Photoshop. You could paint it in a height field, or you can author them using curves. What I mean by map is some sort of user intent to say like this region should be what kind of biome to design that. So that's the standard input, everybody understands that. But if we think a bit more, okay, so how do we work with this thing? What do we actually need to intake? So if you peel over that layer of abstraction, you need to represent the data somehow. The way we want to approach it is for the map, they will be translated to biome attributes. So when you say this chunk of land is a biome, that's a text, that's a string, that doesn't mean anything. If you want to scatter, you need floats, you need vectors, you need numerical values. So we turn that into, would establish some sort of mapping between your, say, what the name of the biome is and the actual numbers that the system can run. Similarly, a thing will happen with the plants. So when you scatter, you not just scatter point cloud that can be anything, you scatter point cloud with attribute that describes not just how tall they are, which way they're facing, but also like, what is this tree? Like, what is this bush? And maybe some colors, maybe you have the same species, but you have different stages of the species, the dead one, the baby one, the one get burned by fire, that kind of thing. So attributes is at the core of it. So stepping back, talking about a little bit of our design aspect of how do we actually design this whole thing. It's a very complicated thing. So the first thing is the most intuitive one. We design for the result. We want a result that looks beautiful, that has subtle emergent behavior. Sometimes it's difficult to get by doing it by hand. That's the nice thing of somehow balancing the artist workflow with simulation. You get that nice natural looking emergent behavior. The other part we need to really be careful is how do you design the workflow, the data flow, down to the point of like, how do we structure this node graph? We don't give you one single node, we give you a bunch of nodes, so different nodes that do different things and they flow different data across. The point is that when we design those, we wanted to make sure that between every two connection, broadly speaking, you should be able to recognize the data as some neutral format data. You can override that, use your own nodes at any point, and then the pipeline should flow as it goes. We also wanted to make sure that memory-wise and cooking-wise, it all makes sense. So I think I can provide a bit more detailed example later for the data flow part. And of course, finally, the most important part is design for the artist. We do exercises like, we design our tools in a normal fashion. Then like one of us will pretend to be an artist and pretend to have know nothing about the tool and start to ask questions of how do I use this and see if all the bases are covered. And when we do that exercise, we do realize, okay, there's a whole bunch of things that's not covered. So that's some of the future iterations we're gonna do. So design choices wise, what's the guiding principles that we're using? We want it to be easy to use and want it to be easy to modify. I already covered those 2 points. And wanted to do iterative development in that sense. So what we're releasing now is an alpha version. It's a vertical slice that goes roughly from the beginning to the end. So you can start with your map and you will get trees at the end and you can bring your trees to your game engine. But it's not the most advanced solver yet. There are a whole bunch of other stuff we haven't done because it's a vertical slice, but you can start trying it if you feel brave. And then we can gather feedback and start to expand later. Usually this is also the development cycle. If there's a central tech team or like R&D team in the game studio who are working on developing advanced tools, what they will do is they don't just hold down for the tool for like 3 years. They do it for a few months and they start to try it out in production and keep going, where the production and the tool development will keep going. So that's what we intend to do as well. Briefly touching on the scientific foundation, we want this to be realistic, so it's not just hand-wavy of imagining how the algorithm is supposed to work. We base it on research. We do different aspects of it. Biome research is focused on when we label a biome, what kind of climate or attributes are associated with this kind of biome. So normal stuff like temperature, precipitation, but there's way more, such as soil quality. So the other part of it is the plant. So it kind of goes in the other direction to see how they match. For instance, we look at a rough plant classification and how does a type of plant get classified to this group. That means they have a certain preferences for those attributes that the climate has. So that would give you kind of a likelihood of like whether this thing is viable at this point. And then we start from there, then we do the scattering and everything else, which kind of brings us naturally to the next point. Now we have all those data points, how do we simulate the thing? So to be fair, this is the most complicated part of research. Those two, the first two are rather well defined, but the simulation of plants are kind of in the CG field, and there are recently some very nice papers coming out, but a lot more work remains to be done. So to explain the whole pipeline in a very simple term, I just reduce it to 3 steps. There are a bunch of nodes. They belong to some of these 3 steps. First thing you need to do is to define what you want. So you define the biome and plant quality, as I was saying earlier, kind of what kind of attribute range they belong to this name, because name doesn't mean anything. It has to be turned into numbers. Then once you have that gets piped in as a definition file. How we handle that is sort of like very flexible. In Houdini, those attributes are stored as geometry attributes, but for the user, we wanted to let the user be able to not open Houdini and change it. So the designers can use it, artists can use it. And also we wanted to make it extendable from the game engine side, so that if you want to write a custom, like a Python panel in your game engine, you want to issue a command or build your own interface that modifies those definitions, you can do that. That means the definition is a dual existence of geometry attribute and a JSON file. So the geometry attribute is optimized for running in Houdini, and the JSON file is optimized for you reading it. In a simple term, we don't use Houdini attribute names in the JSON file. We use very readable, nicely capitalized names so you can see what is what. And we have a single node responsible for communicating between the SOP context and this JSON file on disk. You can also, because it's SOP, you can also save out BGO. It doesn't have to be JSON. If you don't want to read it, it would just be BGO. And every node that depends on those definitions will simply have like a very nice geometry dependency to that BGO, so that guarantees it will be triggered. Assign it. It gets complicated, but basically it's like assign region to the map. The different color, for instance, can mean different biomes. The blue one in the center could be like water body, and they have different behaviors, can be assigned. And then the system will also assign the qualities that you defined to the regions. Then the last step will run the simulation and evolve, and you get a much more granular and nice looking result. So here's some like what we will actually do here. So this is the result of something that's produced by those 3 steps I showed you earlier. So the different species have a nice fade out into each other. And here, for instance, we didn't paint out the water body, so you can see some of the trees are growing in the water. That's because climate-wise, it makes sense, but that's not what we want. So we could just simply modify it real quick by providing a new map. Then the whole system will still behave as everything else will behave exactly how it was, except it's going to remove that. It's just one of the small things you can tweak. So there are some other things. This video is a little bit slow, so I'll try to talk over while it plays. So for instance, you can change the size of the assets with some global control. You can change the spacing, like how close to each other they are. And this is just the vertical slice parameters, so they're not super sophisticated just yet. And this is recorded in real time, playing at a one-time speed. So you could potentially actually evaluate your results in Solaris, so you can get this nice lighting while still playing with the SOP parameters. Because some of the tree, when it gets too dense, you're looking in SOP context, it's very hard to see what is what. All right, wrapping this up, moving on a bit faster. So the point cloud instancing, how do we bring that stuff into the game engine? Well, we could use PCG. We could use Houdini engine. That's needless to say, but let's talk about the PCG stuff we have. We have recently released a PCG Export Swap, and this will store the data from your point cloud that has a mesh ID, so it knows which mesh to fetch in the engine, all the different transforms required, the materials are supposed to attach to the instances, and any kind of custom attribute you want to ship. We can ship quite a large number of custom attributes. So you basically bring something like this in Houdini. Technically, you only need a point cloud with attributes. This is just a preview mode, so you can see which mesh you're actually using, then bring it into Unreal, and you're looking like that, and swap with your high-quality asset. So this is a brief look of what the interaction looks like. So you don't mesh. The copy to point is for visualization. Point cloud is where the point clouds are generated, and the PCG export is responsible for generating that data. And then the data generated by PCG exports will be brought in on the Unreal side using our Labs Unreal plugin. And then all the transform attributes are easy to understand, but in terms of meshes, we use like a mesh array, so you can use a number to kind of pick which one is the corresponding mesh. So I wanted to also mention alternative workflow, which is not necessarily like a tool on the Houdini side, but just a different way of doing it by exporting Alembic. So you could do PCG export as a CSV file into Unreal. You can read that. That's what the previous workflow is. it will run into some performance issues if the point cloud size is too big. So our team find that if you use the Alembic format, it will be more performant for like currently for the cases of like huge number of instances. Moving on to the plugin section. So as I said, Paul has a dedicated talk, so I'll just show you some cool visuals and videos. So the cool thing about this Perforce integration is that it brings the UI, the most useful UI of Perforce client into Houdini UI itself, so you don't have to go to another application. You also don't have the risk. If you turn the plugin on, you will keep track of everything, so you don't have to remember did I check out the file correctly, or if somebody has logged the file. So everything is native in Houdini. It's very easy to use. I tried it myself too. Very smooth experience. So now this plugin is just in SideFX Labs, so you can get it. And you have an option to enable it. It's not automatically enabled. Another super cool one is Gaea 2.0. This is on the back of 5 years of development. The results are very stunning. And they can do very, very high resolution, high fields with super realistic erosion result and all kinds of shaping features. This is just a selection of some of the crazy stuff they can do. So in the past, our Gaea plugin works in a way that you build a preset in Gaea and you save the preset, and Houdini just only talks to the preset and runs that. But the monumental leap that this plugin system has done is that it's not one tool, but a whole bunch of tools where individual options pretty much behave like a Houdini node. So we have basically a long list of Gaea 2.0 nodes in Houdini now that you can just use it if you have the license. Like Houdini height field nodes, you can, as you can see, they just directly interact with normal Houdini nodes. You can, it's very native and very easy to plug into the rest of your system of whatever you're doing. So in terms of user friendliness, it's another leap forward compared to the previous version. All right, the last plugin I want to introduce you guys to is ZibraVDB. Maybe you guys have heard about it. Recently, they were demoing that in SIGGRAPH in the real-time life as one of the 11 selected examples. So it's very, very cool technology. We're currently working towards bringing this into labs. It's not in labs as of today, but it will be soon. We're working on the deployment and everything. So I wanted to first talk about how we used to do things in the past. This is something I did together with Urban Badesco, the explosion guy. So he provided the simulation. I brought it into Unreal using the lab's flipboard textures. So the flipboard texture is sort of representing a whole way of doing things where you fake volume using 2D cards, whether that's for game or for cinematics. So even in like slightly in the past, cinematics cannot afford to do high resolution volume, even though they want it. They're still bound by the hardware they have, and the rest of the sim needs to eat up so much frame time. You can't just give everything to simulation. So in order to achieve something looks nice from a certain angle, we have to do a lot of faking, a lot of shader operations. But if you want to tilt your camera and everything, it kind of just breaks the illusion. It doesn't really work that well. And it only works if it's background elements. If you want the volume to be interactive or in front of the camera, then it just completely doesn't work. Same situation here. In the past, we could get it to look nice, but it's like far away. It's a flat plane. But now we can try something different. So the video you see on the right is done by my intern, Josh Collin, very fresh from like yesterday. It's a Houdini simulation tied to an animated character and brought into Unreal using ZibraVDB and some point lights attached to it, so like all the lighting, everything looks quite immersive. And this whole thing is running in Unreal using the ZibraVDB plugin in Unreal side. So what we're gonna have now is a way to integrate Houdini into this whole pipeline, into the asset authoring and bring it to Unreal side. So what do they have that can solve the problems that we're doing? So we don't have a very efficient way of doing 3D volume representation in Engine. There is Niagara, there is some other plugin that's similar to it, but we know that there's more work to be done. They still eat up lots of performance resources. So if there's any technology can make things run faster or memory footprint a bit lower, that is definitely something that we can jump on board with. They have very high quality data compression in terms of reducing the size of the VDB representation. Actually, the reduction rate is quite stunning. It's actually controllable. It could be something like 30 times reduction or 100 times reduction. If you slide more, sometimes you will start to see like some level of quality, like visual quality reduction. But even sometimes with certain effects, like at 60 times file size reduction, you don't see a noticeable visual difference. So that's really quite dramatic. So you can have a multiple gigabyte of source file. Now you bring it into your game engine, it's only a few hundred megabytes in size. And it is not something to scoff at, because the file size of the game can be quite a big problem when it comes to shipping an actual game. People don't want games to be too big. They don't want to keep extremely large games in their system. There's also a little bit of replayability that goes into it. And people don't want to keep a long game so that they can, because that prevents them from like downloading new games. They only have so much space. So all that has like a long chain of causal effect, and it's all very useful. And the other part is the speed. They have accelerated real-time rendering, both in case of in Unreal and also in Houdini. I'll get into more details about that. So in Unreal, their performance is like 2 to 4 times better than the SVT, the sparse volume texture. That's quite cool. In Houdini, it's also like currently about like 2 to 4 times faster than Houdini viewport rendering if you use the ZibraVDB format. That's because how they handle the loading of the file that stores the VDB. So if you do it in the traditional Houdini file cache way, you have a bottleneck with the input or output of like reading the file. But the way ZibraVDB does it is that they bring the whole sequence, they store the whole compressed sequence as a single file, and they would load that single file into GPU, so you will not have the I/O problem anymore. So you just save a lot of time, especially when your simulation is heavy. Then actually just loading the file takes a long time. Then ultimately, we want to have a streamlined workflow. So working towards that, bringing that into Labs is an easy way, so it's more accessible to you. We will see a video of how that actually works. Basically, you can have like, you set up your simulation, you drop down a node, you one click, it's pretty much word-side file cache, and you end up with compressed files. So in terms of visual qualities and visual features they have, some of these are very, very cool in terms of where they are in the industry of doing the similar things. They can support multiple different lights. The directional lights, point lights, and spotlights are currently supported. And you can also kind of approximate ambient light by just changing the diffuse color. All of these settings are controllable in the engine side. There's a lot of parameters that can change the emission, the density, and everything. So you just need to export the corresponding field from Houdini. Then you can redesign the effect over there. So you can recolor that into something else, not like a black body. The other cool thing they have is casting and receiving shadows, both, and also self-shadowing. So that's super important, because the traditional workflow actually cannot do that. If you do like a card, the shadow, you can sometimes cast a shadow, but it's very like unrealistic, and you can't really rotate it and everything. As you can see, this is like 3 lights casting shadow at the same time. And they have reflections too. So when your environment is shiny, I think this is analytical reflection, so it's not baked anything, it's just on the fly. If you have wet surface, if your material is reflective, and you will just pick up the reflection. So with all these qualities because lighting is such an important part of making sure something looks, it's part of the world. So when you have this, you can very much like nicely blend this into your environment. For virtual production, it'll be super useful. For games, also. So here's what the workflow looks like. Your familiar Houdini setup with just Pyro solver and a file cache. The file cache here is not necessary. You can directly connect the ZibraVDB node to the solver. In case you have a super large simulation, maybe you want to cache it first or something like that. And here you can see it's already compressing on the fly. I got a little bit statistics from them just yesterday, and they tested out like a 7 GB simulation in total. In 40 seconds on a 3090, it compressed down to about 190 megabytes. So it's about 37 times reduction in 40 seconds. So basically you're doing your caching, except you're caching to like a much smaller file. And then if you want to preview that, you can get faster preview experience by loading up that file using the decompress node. So the decompress node will load that single file, put it on the GPU, so get rid of I/O problem. Then basically this part of rendering plus a little bit of our own volume visualization, it's a few times faster than if you just do it with Houdini. So that's super valuable. And then if you are working with Game Engine, you can bring that file directly into Game Engine. It doesn't need an additional level of conversion. It's just the file you just exported from Houdini. It's all ready to go. So you get this high quality result in Unreal. As far as I know, the alternative solutions in Unreal currently doesn't have this kind of visual fidelity. So I'm pretty excited about this.
What format does it export as?
It's a custom format called ZibraVDB. Yeah. So in the past, not distant past, just recent past, they developed the compression technology in Unreal as an Unreal plugin. So basically the whole process will involve, you do cache out the OpenVDB file as a cache, then you tell the Unreal plugin that Zebra has to do the compression. Except that if you're working in Houdini, that's kind of annoying. Why would you want to go to Unreal to do the compression? So you just compress it from Houdini and you get this. This is what we have now with that as part of Labs. You could do the compression, you can export it out, that can go to Unreal to do decompress and render. Or you can just decompress in Houdini, get a faster playback in Houdini, and do whatever necessary conversion you require in the future. In terms of the rendering time, you might be curious, like how do they decompress and render at the same time? According to the stats I know, they spend about like 10% of the whole render time to do decompress, so it's very fast. It's decompressed on the GPU. Then they do the ray matching and everything, plus the additional features. Some of the additional features in terms of like reflection, lighting, and shadowing, that depends on engine. So ray matching is more standards, but those features depends on each engine, how they want to implement that. So all this technicality, all these nice features, ultimately is to be able to bring you something cinematic like this. So this is running in a real-time engine using pre-baked asset, and I think there's some of their runtime simulation as well, because the company also has a different product that does runtime simulation, and this could be like a blend. For like high resolution R-directed simulation, you could done in traditional DCC and bring it into a real-time engine like that. So here's some more interesting stats. On the left side is the original size of the cache, and the second column is the compressed one, frame counts, and the frame time if you actually render that using the plugin in Unreal side. As you can see, some of the bigger ones, the Unreal native technology actually cannot handle it. Also, that's their CEO, Alex Petrenko. He's happened to be in the audience, so if you have more questions about it, you can find him later. So that's the end of my presentation. I'm going to big shout out to my amazing team. That's me, Danica, Hristos, Mo, Bailey, and our two interns, Yumna and Josh. And also special thanks to our external partners and contributors, Business Consultancy, Quad Spinner, which is responsible for Gaea, and Zebra AI, and of course, and SideFX R&D team, who provided lots of invaluable support for our own tool, but also the partner integration.